Hi everyone. My name's Nigel and I'm based in Ireland. So I work for a company called Cloudsmith and I work in developer relations. While we're not talking about Cloudsmith exclusively for this session, we're rather focusing on Helm, the project itself, and identifying insecure configurations or vulnerabilities within public Helm charts. So with that, I'm just going to jump straight into it. Just click next. What is Helm? I'm guessing most people here on the session already know what Helm is, but for those who don't know, think of apt or yum, these package managers you see in Linux. Helm is effectively a package manager, much the same as those, but it's for specifically for Kubernetes. So it was designed in a way to easily package different configuration files, which are all YAML based. It was originally created by a company called Dace Labs. It's a CNCF project, open source. It's one of the many projects that Dace Labs have put together. So yeah, why Helm? Why is this such an important topic today? So Helm charts are essentially a really great solution. They allow you to manage the Kubernetes application, upgrade it, deploy it initially with ease. So you can configure it, you can put in different you can deploy different apps, actually several different applications within a package. So you can be quite granular about what you deploy. Now, the very nature of that, because it's so easy to package and update, make changes to it, oftentimes you have these large packages that have many different dependencies. These could be container images, you could have third-party libraries, all of these could be packaged within a Helm chart. And naturally, the more you add to a chart, the more natural security vulnerabilities can show up within that chart. Therefore, it drives a real need for us to be able to monitor the dependencies or vulnerabilities within those Helm charts. Again, if we want to meet regulatory compliance standards, we need to be able to swiftly respond to CVEs, so the common vulnerabilities and exposures within those charts. So yeah, what are the security considerations around Helm? I underscore that 9,000 charts available on Artifact Hub. That number has probably changed quite a bit. It can only go up. So my point is there's a heck of a lot of potential packages out there that we can't fully trust or fully understand what's contained within those. So the challenges lie in the fact that the Helm charts are often managed by third parties. Within that, it's not entirely straightforward for us to be able to be notified or understand when new versions of a chart with underlying dependencies are actually presented, and if they require a security fix. It wouldn't be realistic for us to manually change or manually check the change logs associated with those charts. And certainly monitoring for updates for these channel charts is rather impractical. So if we're talking about environments where we have, high uptime and there's rapid response where a lot of things are changing fast, and that essentially sounds a lot like Kubernetes, we need to have a kind of a strategy around what we deploy and making sure we're applying these best practices. So while Helm is, fantastic, you can see from the commands on the outside, it's really straightforward for you to say, point to a repo, install the chart associated with the repo, and even the uninstallation process is really simple for those charts. That very convenience nature of Helm is what is creating the pain points that we're going to talk about now. So what are those common pain points? I think the first one, while it seems fairly obvious to probably most people who are attending, is insecure configurations. So what I'll say around this is that it makes up probably the bulk of the security issues in Helm. Simply put, you know, someone's, you know, someone has created a Helm chart. They haven't designed it in, your organization's considerations around it. So what I mean by that is, someone would prepackage a Helm chart and they say, look, it will deploy a thing, and here you go. The security considerations are up to you what you do with it there. So it's designed in a way that it works as is. Now we'll point to a Microsoft security research findings in a while, but that very nature of, hey, we package something, and as you can see in the example here, you have an RBAC, the role-based access control YAML file, and it's basically just giving these wildcard asterisks to say any API group, any resource, any verb, like create, read, update, delete, those CRUD actions, we're allowing them. And the idea behind that is if it's designed to work as is, it means no matter who you give it to, this Helm chart's going to work. It's going to work exactly out of the box without any fine tuning required. It's up to you then to consider the security implications around that. So things like RBAC rules, resource constraints, network policy enforcement, those kind of things, because the developer of the Helm chart, as I say, it's third party, they don't understand your environment, they're hardly going to implement, strict controls for that. And just one last point there is again, that opens up a huge blast radius where naturally, if you have elevated permissions or you have no network implementation or control there, if the chart or the application associated with the chart is compromised, naturally they have a good chance of moving laterally in that environment. The second bit is exposing sensitive information. Again, I could repeat myself several times by saying this isn't, it might seem obvious, but it's something organizations do today. So as you can see, the part where I highlight in yellow, I basically said, here are some credentials and they are in plain text and they show up inside the chart. So hard coding those sensitive credentials is obviously a bad idea. If a team were to expose those credentials, they would show up in version control, CI/CD logs, public repositories, that kind of thing. If they were to show up in a public repository, then naturally an adversary and an attacker would be able to gain access to your environment through those plain text credentials. Without saying it, that obviously increases the risk of data breaches or even just breaching compliance controls like GDPR and HIPAA compliance, and amongst many, many other. I highlight then in a green the improved scenario. So in this scenario, what we're doing is we set the actual password stored within what's known as Kubernetes secret, not in plain text. The value YAML file that we're referencing then contains the secret, preventing accidental exposure. However, what I will say is that what you see there, the encoded password, it's in base64 encoded. While that's an encoding algorithm, it's not actually encryption. So it's not very hard for someone to still obfuscate in a way, or sorry, to decode it in a way that it can be read. So despite its name, Kubernetes secrets are not secrets. They're not actually encrypted in any shape or form. So while this is a long topic and I don't intend for it to be the topic of this session, I do want to say that there are solutions for encrypting sensitive credentials when it comes to Helm charts. And these include things like Helm Secrets, which is a plugin, HashiCorp Vault, there's Seal Secrets by Bitnami, SOPS by Mozilla. There's a bunch of different solutions for that, and those would be the things for making sure that sensitive credentials aren't accessible. This is always a fun scenario. It's one that I feel like not enough organizations talk about, and it's around the dependency vulnerabilities. Like I mentioned, there's a whole bunch of different things you could deploy in a Helm chart. So it could be a front end, a back end, some intermediary microservices that talk amongst them. And all of those individual things can contain vulnerabilities naturally. What I'm focusing on here is a thing called the dependency death loop. So this is obviously a huge headache that an organization would want to avoid. Circular dependencies between the Helm release resources obviously should be avoided. And that's where they are relying on each other, depending on one another. So in this case, the backend and Redis, in order to start. Now, in this case, the interdependent Helm release resources will never be reconciled. And the reason for that is it's depending on one another. So okay, to simplify this, what's happening is we updated the backend service YAML. We added a dependency config, which turned the scenario, like you can see here on the right side view, that graph or diagram. Once we applied the manifest, basically you can see here we used the flux to check the status of the Helm release and the associated dependencies. So what we can see, even if, sorry, in the bottom left corner, what I'm using is Kubernetes events to check the reason for the Helm release, actually flagging it for not ready. So there's different ways you go about this. You could describe the Helm chart too, but basically what we're trying to do is check the reason for why they're not starting up. So in this scenario, the dependency loop never gets resolved because basically each dependency is relying on the other dependency to get going. So again, more and more organizations are talking about creating things like super Helm charts, which are great. You package all these different things in it, but if you just design it, this isn't a CVE we're talking about here. This is just a misconfiguration where we say two dependencies in this case are reliant on one another, and what's that going to do is crash the application in production. So obviously not a great thing to do, but it's also, creates a realistic attack surface where our application is no longer running, and then we have to investigate why that's not running the way it's expected to within the Helm chart. Um, Four, I guess, is a section around RBAC. What I'm trying to do is provide the links there for the actual Helm documentation around this. Um, so what this part's pretty straightforward. So what we're saying here is like RBAC is, yeah, one of those things everyone's all heard of, role-based access controls. It's where you can set, for instance, create, read, update, delete, those CRUD actions. So what you can and can't do. And you can assign those to users, so roles, and you can do this via role bindings, which we'll talk about on the right side view there. Now, improperly configured access controls to obviously could lead to unauthorized access within your environment, but it also can lead to potential privilege escalation within context of Kubernetes. Over permissive roles or permissions can provide unnecessary access to sensitive resources, and improper access controls can even result in privilege escalation, as we mentioned there, across the entire cluster. So what we're trying to see here is that in the first YAML example, what we've done is we've defined the RBAC role to say you can do specific things, for instance, the verbs. So in this example, it's basically got access to do whatever it wants. And you notice how it's get, list, watch, create, update, patch, delete. The resources they're tied to, so you can do all of those verbs against the resource, which are things like pod service deployments. And then you could even tie it to an API group. The binding is what you tie it to a user. So let's say we've created a user. In our case, the user is called Helm user, and that's tied via the Helm role binding, which is the binding we've created. It's its own object, and it's inside the namespace Helm namespace. So obviously you give it your own real namespace name. So that's basically access control. It's not something that any organization, for instance, when they create these Helm charts, they don't know that you have a user in your user group called Nigel. So because they don't know them, they don't know the name of your network namespaces. Generally speaking, it's going to have like no specific controls or wildcards around things like verbs, resources, API groups. And therefore, that's a lot of permissions that someone would have with that chart that isn't configured correctly. The next one is pretty, I think it's pretty important, and it's something that organizations are subject to making mistakes all the time. It's risk around altered or malicious charts. So again, while it does seem obvious, what you're checking for here is the reliability of the chart. So you can see here I've highlighted on the Nginx from Bitnami example that it has 90 stars. So that means it's like 90 people have positively said, I believe this is a good project and it's trustworthy. So that's something you can go by. Another thing is you also want to look at, for instance, like whether or not it's stale. So you can see, for instance, some charts like this Falco rules one. Now it hasn't been updated in 4 years. You could look at that and go, okay, if it was, for instance, potentially compromised or there's a vulnerability in it, there hasn't been a change in 4 years. So that's something that could be sitting around for a long time. Now, what Artifact Hub, this is where you can get all these public facing Helm charts from. You can filter it by specific controls. So you can filter it down by is it an official chart from an official project, or does it have verified publishers, or is it something that's authorized or approved or published by the CNCF? These kind of things are also great controls to be able to say, I only want to use it from an approved source. You can see so often, like in the case of that Nginx one, that it's a Bitnami chart apparently for Azure Kubernetes Service, AKS. You can see it's from Joaquin Toe 2051. Now, do we know this person? Probably not. And if we don't trust them, would we honestly pull that chart and actually use that in production? Probably not. So that's one thing is like verifying the authenticity of the source. So we're not just pulling random things from the internet that could be potentially compromised or malicious. And then the other side of it is Helm wasn't designed in a way like it's designed with so many different features that you can check it for provenance, you can do checks for change in the project, you can audit it, you can do all sorts of cool things, but it lacks automated scanning. So I give an example here where what you could do is you could run the Helm template, which is the template check, basically check the content of the directory, which is my chart, pipe in Trivy, which is a CNCF project. And what Trivy will allow you then to do is do the CI/CD pipeline scan. You know, it can be you can scan a bunch of different things, but in this case, we're using Trivy to scan the contents of the my chart directory. And it's using specifically the Kubernetes version of Trivy. And it's doing then security checks on it. what it's telling us is basically those controls we talked about earlier. Are there hard-coded secrets presented within the chart? Well, you can check for that. Or does it contain the hard-coded secret within a specific file? So we also want to know that so we can prevent that going forward. So Trivy is a brilliant project, very popular within the CNCF ecosystem, no different to Helm itself. So in this case, what we would use is Trivy, pipe it into the contents of the Helm template output on that file, and then you should be able to see, for instance, are there insecure configurations that we could take action on. Um, the alternative is, as I mentioned there, there's that process where I piped in Trivy to scan the contents of that file. That was quite a manual process. I could certainly do it against different directories and all of that. But you got to remember, if we're dealing with a large number of packages or artifacts, and we're not dealing with just Helm charts, there are so many different artifacts of different sources across your ecosystem, that process doesn't scale very well, becomes a little bit tedious. So what we can do with my company, with a platform called Cloudsmith, what you can do is you can actually push artifacts of all different sources, supported formats. So for instance, Python, you could send Ruby, you could send, in this case, Helm or container images. You send those to the artifact management platform, and then from there you can actually perform security scans, which is effectively just Trivy scans, or you would also, aside from having CVSS scores, you'd have EPSS, so exploitability score. So these are kind of the cool things you could do around scanning a large volume of different formats and checking for those artifacts to see do they contain vulnerabilities, just like the example we showed there, except rather than doing that as a manual task or something I have to keep doing checks on, you could have it as something that every time you upload packages going forward or push them to, when we talked about there, we're pulling a public chart from Artifact Hub, then we push them to Cloudsmith, and then it can perform the scan on automation on as part of the process of pushing it to the Cloudsmith repository. So going forward, rather than pulling random packages from the internet, you would pull them from a secure repository like Cloudsmith going forward that you know has been scanned appropriately. So yeah, that was all a lot of stuff there where I was just talking about these are hypothetical, not hypotheticals, but things you should be considered of. Let's tie it to real world incidents. And ironically, the first one I start with is a hypothetical one, but I still think this holds true. So there was one that I found publicly documented on the internet. It was around ChartSploit. In this example, you can see that there's an external URL value that's mentioned there, and it's not properly sanitized. So those familiar with like SQL injection or like cross-site scripting, they'll often talk around sanitized or unsanitized fields. So this could obviously lead to an injection type attack. That's basically where the attacker could potentially exploit it to execute arbitrary code or exfiltrate data against the config map. So this case, we have a Helm chart. It renders the config map. It generates the config.json you can see there under the data field. And it inserts this external URL directly into the JSON using this Go templating, which is the values.external URL inside the brackets. If the user sets the value in the values YAML file, or via the CLI, that's something else you could consider doing. It gets rendered without validation or basically doesn't contain the escape. So that's something someone could realistically do. What I wanted to also check to see was like, how does it differ from like other real world CVEs, for instance? So this one, which I only found recently, was actually dating back to 2022. So it was the Apiro research team that actually discovered this. Now, although this is to do with compromising Argo CD, which is deployed via Helm, the actual interesting thing here is how they executed the attack via Helm. So in order to build a new deployment pipeline, the user in this case, they were able to decide they could have either defined a Git repository or Kubernetes Helm chart, which is one of the options that they facilitate here. So the metadata and information needed to deploy the appropriate Kubernetes configuration and the ability to dynamically update the cloud configuration could have all been done via this chart. At the end of the day, you got to remember that a Helm chart is basically just YAML files embedded with different fields and forms and declaration. So if you wanted to declare, you want to say what are the resource configuration, what is it that you're going to deploy, You do all that via Helm. So the application in question here, which is the Argo CD example, contains values of many sorts. One of these examples contain file names and relative paths to self-contained application parts and other files. So this is something while has been addressed and it's, long gone now. That's a 3-year-old CVE. It's interesting how Helm can be used as something to allow someone to basically hop to other applications within their ecosystem, as seen here. Um, Another one worth mentioning here is just really ongoing recent research that's relevant. I mentioned that was a 3-year-old example there. Um, in this case, this goes back, what are we on the 20th today? So that's 15 days ago is when this research was published by Microsoft. So two Microsoft researchers there was Michael and Yossi, and basically what they did is they identified a bunch of different projects out in the wild that are potentially exposing services externally, which was something that becomes a recurring topic, but also where they don't have this like built-in authentication or authorization by default, um, which is totally understandable. Like a lot of open source projects contain in a section, and we'll come to this in a second, which basically explain how the project can be deployed out of the box. As we mentioned earlier, that's where you're supposed to configure the security part yourself. These documents often include default manifest, as explained. They have predefined Helm charts, which are, again, it's all around ease of use to make sure they're all working as expected. Um, Now, internet exposure in these cases can be done via load balancer services, which is something that becomes a recurring topic. And that's because it allows for external IP with direct access from the internet. Or you could do this via ingress objects, which is also similar, but it's HTTP or HTTPS traffic for internal services. Um, Now, if we don't configure properly authentication around them, you could basically allow insecure access. That's the way it goes. So I'll jump to those examples that the Microsoft team found. The first one is around this Apache. I don't know how you're supposed to pronounce that. Is it Pinot? But this project basically puts out, here's our way of deploying Helm. And you can see it's running Helm with pre-installed packages, all pre-installed, it's ready to go. And in this case, there's a quick start and you could just copy that and paste and it will definitely work. That's the way these projects go. So you can see in the documentation here, while Apache Pinot's documentation states that this is provided as a reference setup, um, this was actually vulnerable to this issue where they're deploying. I don't know if it said it here on the previous chart. They deploy it with, oh yeah, it doesn't show it there, but it deploys where it creates the load balancer service, and there's no authentication on this mechanism. So that's pretty frustrating. Now, it's not just the example we mentioned here where you have Apache Pinot with default configuration that requires further guidance. Now, this is an end user solution. So, for instance, you're not developing, well, you wouldn't think about developing on Apache Pinot. You think, I'm just deploying it because at the end of the day, it's a real-time distributed OLAP data store. It's just something I use for querying large-scale data sets with low latency. That's what it promises on the box. So in this scenario, we're looking at other tools that have done something similar. So we can see here that there's two services allowing unauthenticated access to query data store and manage workloads. So to understand how all this happened, how they found these examples of these misconfigurations, the Microsoft research team, basically what they did is they used GitHub code search repositories. So it's where you can put in like, show me examples for this project. That is Helm. That is using, for instance, things like load balancer or ingress or all those kind of search terms that they're checking for. So just basically free match string query searches. They sorted the results with the popularity and deployed the application in controlled test environments to assess the default security posture. Now, the actual goal in this scenario was to find out the applications that are exposed to the internet by default. That's the simplest way of checking for it. And more critically, I guess, than that is they want to check whether it's incorporated any form of authentication or authorization mechanisms. So they weren't going looking for Pinot. Basically, they looked for tools that had these vulnerabilities. So the majority of these applications evaluated at some point that they basically lacked some form of password protection, which is pretty frustrating. And then a small group of those didn't provide any authentication at all, really, around that. So what we noticed again around Meshery was this another example of it. Several apps within Meshery seem straightforward at the beginning, but what happens is you have this whole default by convenience, I guess, logic, which is, it just does the external, or was it? I think it was load balancer in this case, is how it's configured. But either way, you have an insecure workaround by default. It's something you're supposed to actually fine tune. So in this case, many in the wild exploitations of container applications originate in the first example that we mentioned of those 6 steps that you need to take action on, which is basically misconfigured workloads. Um, like it's with Helm, you think when you're deploying an application, it's all packaged in a way that, okay, I just run it and that's fine. But actually, it's just another part of your supply chain that we need to actually be doing fine tuning on. So in order to take action on this type of scenario, what you need to do is basically review before you deploy, even in those examples that we saw there for the quick start. This may require, like we saw there earlier with Trivy, which is doing regular scan of your organization for exposed services, or actually a simple way of doing that actually was via um, the GitHub code search example that we showed there a second ago, and I'll come back to that. And then basically monitoring those container applications as well, just to see what is network, what is exposed, for instance, to public internet. Um, yeah, and this is actually the query we'd use. So in the top right corner, see where it says github.com/search, and ignore all the like percentage marks, but basically check for anything where it's ingress, load balancer, node port, Selenium hub, these kind of things, and check for YAML. It's worth stating that in this case, while the official Helm chart for Selenium didn't actually expose it to the internet, there were other projects that were, and these are just as possible that someone's using those examples. So I'll jump to the next slide here, where basically you can see that query that's run at the top, where it's looking for things like Selenium Hub, language YAML, load balancer, node port. In the case of using things like node port just without any context, just I will deploy Selenium Hub that way, you can see other projects there like .NET Conf 21's workshop, which I'm guessing was maybe to do a workshop with this exact security consideration, or Kubernetes Docker Selenium. That might have been this person Manoj. Maybe they were doing something that they wanted to share amongst their team, but in essence, these are showing up as insecure configurations. So when you think about it, like when we look at Shodan scans with these public scans, we see like a huge list of different applications, Redis, Elasticsearch, Prometheus, go on, basically keep resurfacing with these kind of insecure by convenience configurations. So yeah, that's just basically one thing I would show off there. So how can we take action? That's probably the most important thing we're going to get out of today's session is how we can take action. So Helm lint is probably the most obvious thing we can do. What we're using is Helm lint basically allows you to do error catching, I think is the bit safest way of putting it. Error messages will show up, you see here, where it's basically causing the chart to fail installation. So if we're doing something wrong, like for instance, we haven't specified a version that needs to be, it's a basic requirement for the package, we can use lint to check for those obvious errors, and then it will throw it saying, look, you need a version in order to actually deploy this application. So it'll crash it, it'll fail. Warnings are basically suggesting issues where you deviate from best practices. So although these are not your common thing that's going to crash your application, they are best practices recommendations around making sure applications are more secure. So we should definitely be factoring in that. We can obviously integrate this lint action into our CI/CD pipelines. And that's great because what it allows us to do is essentially provide another static analyzer similar to Trivy, but in this case allows us to identify or fix potential problems as opposed to does it contain a CVE. Consistent versioning is an important thing here. I know there's a lot to look at, but basically, if you're using everything that's latest, how do you know like what the version is that contains the problem? So, it's important that we have version control, and obviously in the case of Helm, since version 2 of Helm, and that would include version 3, it now adheres to this Emver you can see here is the logic of major, minor, patch. So it should be like 1.2.3 is the logic you can see there in the bottom right corner or bottom left corner for the Nginx TJZ file. So in this case, what happens is the packages and the repositories are identified by the name of the package, whatever it is, plus the semver versions. But the idea behind keeping a decent change log is if we see something that's wrong, we can always go back to these chronologically ordered packages that we can actually rely on or trust that have specific app versions or versions assigned to those. So once we identify where the problem came from, we can go back or forward to make sure we're not, subject to that vulnerability. Chart tests are another great thing to be able to do when you're actually making sure your applications are more secure. If a chart contains a number of like resource or components, that we mentioned earlier that all are interlinked. Basically, in the case of the chart author, which we all are now at this point, we want to write some tests basically to validate that our chart works as expected, but before we publish it or while we're installing and testing it. These tests can also help with the consumers, maybe that's our customers or end users or teams members who are using these charts, understand what the chart's actually supposed to be doing. So a test in this case, when we use Helm test, is basically lives under the templates directory that you specify within the chart. And it's just a job definition. It actually runs as a job. And it specifies a container with a given command to run. So you can see here when something fails or whatever, you can see it running as a web app test in the bottom right corner. It does run that test pod. The container will exit with the exit 0 if it was a success, and the job should throw, I guess, a test, yeah, test failure if it's obviously a failure. The main thing you need to know there is you define as an annotation with the elm.sh hook with test. And if you've specified that into the manifest in that YAML file for that pod, it will perform the test. So it's a great way of accepting something, as this is not adhering to our best practices. Software provenance, though it seems pretty obvious, is the way for us to verify the origin of the package. Helm provides a way of doing that. So it's the Helm package sign when you want to sign it off. They use tools like PKI, GNU, PG, all sorts of different ways to basically generate and verify the signature on the files. So you can see that SHA-256 is the unique identifier associated with that file. So it has been that provenance that it's basically signing it off, that it's authentically you that created it or owns it. So basically when you do software provenance, when you sign, basically you get the TJC file, but you also have a .prov file. So when we cap the .prov file, you can see the file within it that's actually got the provenance on that, the check. These are generated when you use the sign command, and if you want to verify them, you use the --verify. If the keyring now that's contained, I think when you sign it, you obviously need to know where it is that you specified it. It should be maybe in the default location. I guess if you don't have that, you would specify and I don't think I mentioned it here, is the --keyring path, just to make sure the path is explicitly mentioned when you're doing the Helm package. Basically, if verification fails in this case, the install won't be allowed to go through. Like you need to have it signed off by the appropriate owner. Monitoring logging, that seems pretty obvious, but in this case, well, it's not obvious actually at all. So what you want to be able to do here is make sure that we're using Kubernetes audit as a way of auditing, say, for instance, certain metadata. So in the case of Helm, to understand what's going on, you can set up a centralized output via fluentd to send it off to a specific endpoint. These are all great things you can achieve. So in Kubernetes cluster, in this case, would it be able to generate, for instance, user application activity via the Kubernetes API. And again, it's just a great way of understanding what is happening with the Helm charts. And yeah, then one of the things you'll probably do once you start doing all these manual tests is you want to automate pretty much everything at that point. So the Helm project itself actually provides a project, a repository for chart repo actions, GitHub actions, I should say. So if you want to, for instance, do your own test, like you can see here, we've got this run a chart releaser, which is a GitHub action sample that's provided. You can do that via that repository. These are great samples to start building off of. And again, you want to do automation around things like testing, version control, signing, releasing, all this kind of stuff will eventually be done by GitHub Actions because it's all about doing this in an efficient and timely way rather than doing slow manual processes. So they provide examples around that. Now, I know we're probably good on time, so I do want to leave some time for Q&A. So what I'm just concluding with really is that you want to be able to verify the authenticity of the packages. And again, we talked around provenance there a short while ago. Unused releases, if something is no longer being used, it's irrelevant and therefore stale in your environment. Consider uninstalling it. Helm provide great documentation on doing all of this. There should be a culture of avoiding blind trust. So basically, don't use packages you don't trust from the public internet. And try to, before you actually install it, is pull down that chart, that repo, and be able to like investigate before you apply. The main goal, especially if you're maintaining charts, is to keep the charts updated. If you're not maintaining, if you're using someone else's, then naturally you can also just use Helm to upgrade and make sure that you're using the latest version of the Helm binary as well as the associated plugins. As we mentioned, base64 encoding wasn't actually encryption. There are tools and processes for that, but even that encoding scenario provided there is certainly better than just putting in someone's password in plain text on the internet. And then finally is just secure repositories. This isn't a sales pitch for Cloudsmith, but what I'm saying is if you don't do it today, there's certainly benefit in considering implementing artifact management as a solution for basically pulling in these custom packages or public packages, artifacts into a centralized solution, whether that be public or private, to perform, for instance, the provenance checks, to perform the scanning for vulnerabilities, or just licensing conflict, whatever it is that's relevant to your organization. I provided two last bits as we close out here, two last resources. One is actually a blog we only published yesterday on platformengineering.org. It's probably in the Slack channel. I don't know if people can access that. But either way, you can scan the QR code or just go to that URL directly. And the last resource there is an ebook that we have published at Cloudsmith, but it's for anyone attending. It's free, so you don't need to pay for this. I wouldn't want you either to be paying for it, but you can scan that QR code and you can download that ebook. But again, it ties into the broader topic of CI/CD security risks outside of just Helm and making sure that you can enforce, for instance, great GitHub action automation and stuff like that around CI/CD. So with that, I do want to leave time for Q&A. So I'm looking at the questions that are coming through. There's nothing in the Q&A part. Oh, no, there is. Dean Barron said, great talk. What's your take on maintaining and upgrading Helm charts after we've installed them? How important is it? How often should it be done? And how should it be done? Yeah, there's no straightforward answer to that regarding I think the main thing you'd want to be doing is once you've installed charts, can you, for instance, inventory them at basic level? Can you audit, for instance, what are the charts that you have? Now, it's great, like with Helm, you can check for instance, what are the charts that are active? For instance, what are the associated dependencies within those, as we talked earlier? But it's important to also just have at the holistic level, what are the things being run by different developers and different organizations? What's running in my machine versus what's running in production? And then also being able to make sure, okay, when we've done that, do we have a source of truth? What are like for instance, we're sharing different packages with many engineers in different locations. Is this the one that's vetted, signed off, and approved by your organization that we trust this one? Like for instance, your security team, DevSecOps would say, this is something that we're confident we've done those checks, and therefore our engineers or developers should be using this chart versus we're doing that cycle over and over again, which is pulling down charts, doing manual scanning, and so on. That would be pretty tedious. Okay, I'm also seeing Brooke saying there's a bunch of cues in the chat, so that's
Yes, we have a few. Um,
yeah. Do you want to pick out one that stands out to you, Carla? Sorry for leaving
Yeah,
this.
no worries, no worries. I mean, whatever you prefer. But yeah, there is a few questions in the chat I can see. Maybe we can get this one. Could you please share recent Kubernetes vulnerabilities and top mitigation techniques?
Yep, that's a really good one. Share recent Kubernetes vulnerabilities. I mean, the best one is, okay, there's a few resources around this. We actually just mentioned there the OWASP guide, but that was specific to CI/CD pipelines. There is a project called OWASP Top 10 for Kubernetes. What that will do is it categorizes the top 10 by risk configurations in Kubernetes. It will tie it to known CVEs where possible, but it also, unlike just listing CVEs for you to take action on, it actually says, here are the mitigation strategies. I think that's a great resource to start on, which is saying, okay, if we're going to take actions to secure Kubernetes, not just Helm, but our whole Kubernetes environment, that's definitely something to take on with mitigation action. Other than that, if we're just talking about Helm and understanding what are the common vulnerabilities associated with Helm today that are being disclosed, the best thing to do is actually just look at those CVSS reports, those NIST reports, to basically say, what are those CVs like I highlighted earlier, the one around Argo CD. I hope that answers the question. There's a lot of great questions here, so I'm trying to prioritize without prioritizing, if that makes sense. How can we verify that the Helm chart is not vulnerable to attacks? What steps should we follow to perform this assessment? So I think what you're referring to is the part around sanitization and sanitizing fields. Um, that's a really good point. Like one thing I will say is the Trivy that was doing the checks earlier. That's a great tool for checking. For instance, we say, did you expose credentials inside that chart configuration? Great, that would be something that's subject to attack. Or, for instance, does it contain a Docker image, something we could scan and say, does that Docker image, which is referenced within the Helm chart, also contain a CVE? So that is something you could take action on, which is say, well, I'd rather not use that version of that Docker image, which is vulnerable because that is something I'm going to deploy via Helm. So these are actions you can take as well. If it comes to like misconfigurations and you're not adhering to best practices, like I mentioned earlier, doing things like the lint checks, which is to check for things that deviate from best practices, these are all things you can start doing. But like I said, that's something you would start doing on, for instance, a package that you don't know anything about and you're testing it out, which is pulled from the internet, or you're starting off one and you're making sure it adheres to these best practices. Once you've done that, you probably want to start publishing it to a trusted, secure repository, like something like a Cloudsmith, so that in future you have that point of trust, that thing you can use a lot going forward. Um, there's one there, how to verify that the Helm chart does not perform egress calls to sources that you don't want as an organization. Is that through scanning our network policy on egress traffic? There's a few ways to do that. I used to work for a company called Tigera, but it's a lot similar to another company called Isovalent, so this is not a sales pitch for either. But what these platforms, what they provide at the end of the day is they provide a CNI, the container networking interface, and then they also provide the network policy implementation. Whether you set up the network policy or not to basically block that egress that you don't want, those CNIs you can basically monitor, whether it be from eBPF or you're just looking at IP table traffic, to basically say, what is the source thing, the application that's making those outbound connections? And then you make a kind of it's a pretty educated decision to say, well, that egress traffic, which I would never trust, and I don't understand why it's talking to that third party service, is coming from a pod that I deployed via Helm. Should I go back to Helm to see what the configuration looked like? And that is something you can do. But the best place to start is start looking at whatever the CNI provider that you're using, whether it be Calico or Cilium, and use their network traffic analyzer. Usually they have some form of free analyzer, which you basically can start monitoring what is the outbound traffic on that. So that's something you could definitely implement today. Um, how do you scan the chart with? So a question by Bar. The example I provided was two things. There was the lint scan check for the actual configuration of the Helm chart, and then the other was just Trivy. Trivy is definitely like a popular open source tool. I'm not involved in the project in any way, but that's something I would have used to pipe into the chart configuration to see where those insecure configurations occur. Are there any other auditing tools that run Helm chart and show all of the open ports on the container versus just what is mapped in the Helm chart? Is there any pretty exclusive to Kubernetes network security programs? Um, that's a loaded question, but basically, are there tools To run a Helm chart. Yeah, like what I definitely that goes back to the network security part. Like if you have, for instance, one of these CNI providers, they're a great way of the second you deploy something, they will give you all that insight into what egress traffic is on those workloads. So you can definitely make those decisions. But then it always ties back to, okay, if it's doing that because it's an insecure, it's a badly, like, sorry, the container image is the problem, then you want to swap it out with something that you can trust that would mitigate that issue. Like it's a compromised image that you're referencing in the chart. Um, or it could be also in the configuration of the chart itself. But either way, you can make that informed decision once you start monitoring, but you have to deploy it in that case to test it. So that's one of those scenarios where you don't test something blindly in production. You probably want to test in some form of staging environment. Um, yeah, so I think last question is it a good practice to deploy an API management server, safeguard the KS pod? Yeah, absolutely. So, whether you're using something like Linkerd, there's Istio, there's a whole bunch of them, even Cilium have their own service mesh, if that's what you're talking about. Those kind of solutions are a great way of monitoring um, layer 7 traffic that's going on. So you can monitor that. And then also we mentioned there the CNI providers can look at your layer 3, layer 4 traffic as well. So definitely worth considering having visibility and control into network and yeah, HTTPS traffic as well. So yeah, I think that answers all the questions, I hope. I'm glad that everyone had a beneficial